Today let's talk about pre-compliance radiated emissions. We measure pre-compliance radiated emissions throughout the design cycle as you improve your product development. Early in the process, we use near-field measurements for debugging and finding root cause. We can also use reproducible setups and studies to compare from revision to revision as we make improvements. Near the end of the design process, we might use far-field measurements to better approximate full compliance testing before you go to market. Let's first look how to set up a near-field measurement. Here is our DSA 815 spectrum analyzer in its default setup. So what we're going to do is show you a couple things we like to set up and change before we make some EMC measurements, and then look at what those look like. So the first thing we're going to do is go into our attenuation menu, our amplitude menu actually, turn the attenuator, internal attenuator down, and turn the RF preamp on. This is the best setup for these kind of measurements because it gives us, we have a fairly low signal level, and it gives us the best way to measure those. We're also going to change our frequency so that we're only looking at DC to 500 megahertz. For this test, we don't need to look beyond that. Now we're going to take our near-field probe, which we have on an SMB connector so we can orient it and pivot it, and then connect that into our spectrum analyzer in the N-type connector on the front here. Now we can start to make some measurements on this board. Start to see some different peaks. So here on the micro, we've got some spurs from a clock. So those are spurs up to about minus 60 dBm. We can look at those there. We can also, if we want to change this a little bit, we can change our trace mode, trace type, to max hold. So what this does is as we look over the entirety of the board, we can see where all the peaks are, and it basically holds the maximum value at each frequency for us. So there we see some DC noise in that area around the power supply converter, and we see our primary signal peaks in the 100 to 500 meg range coming from the micro. So let's switch it back to a live clear write mode. We also have our software toolkit here. This is Ultra Spectrum. This is sort of the standard PC based user interface. So it gives us some nice options as well. So here we can see a waveform intensity chart. So over time we can see the values change as we look at different parts of the board. We can also see a peak list, which is going to be important later on as we do some more standardized and advanced testing and zoom in on those areas and do further testing on what the values are and how important that's going to be. So there we set up a basic near-field measurement. To improve the results, we reduced the attenuation, turned on our preamplifier, set our frequency span, we used trace types to stabilize and compare readings, and we can also use Ultra Spectrum to show the waveform waterfall chart for more time-based analysis. Now let's look at how we can do more comparative tests using a standardized setup. Alright, here we are back with our spectrum analyzer again. Now in our first test, what we did was we were looking for some hot spots on a board, and we were really testing in a early design phase, right? So now what we want to do is, as our designs process, we want to make a little more standardized measurements. That way we can test for some repeatability, we can test for changes from revision to revision of our boards. So what we've done here is we've set up our test a little differently. We now have a holder holding the probe in a specific place and our board marked out on the table so that we can compare a couple different board revisions. And this is basically what we were looking at before on our first board. So this is our early rev board that's showing some EMI on it. We're going to do a couple things as we advance this testing here, just to do a couple things a little differently. We are going to go into the sweep menu. We're going to put it into a little higher accuracy mode. We can also adjust our bandwidth in the RBW mode. By shrinking the bandwidth, we can get a little lower noise floor, see a little more peaks. It does slow the measurements down, but again, because we're always taking the measurements in one place, we don't need a measurement every 20 milliseconds here. So So now we can see that. We can also, just like we did before on the software, we can use a peak table here on the instrument itself. Capture those peak values. Those are again going to be areas of concern later. So that's one thing we're going to do. And then again, we can also use the multiple traces on this instrument. So what I'm going to do here is freeze this first trace. And we can see here that we had the kind of similar noise up to about minus 60 dBm. Now we're going to use trace 2 to overlay that. So we see very consistent data with this board in this particular setup. Now what we're going to do is remove this board and bring in a different revision of this board. And so we can see here by the difference between the purple and the yellow traces on the screen, we've made a significant advantage in the new board rev. So this board rev has significantly different profile, lower peaks by about 20 dBm. So as you continue to build on your design phase, you can monitor and make changes and test the relative accuracy, or test the relative EMI output of these of your product as you get closer to going to market. There we saw how a more reproducible test setup allows us to compare measurements between board revisions. We can use RBW settings to improve signal level and traces to help compare on-screen between versions. Next, let's look at how the S1210 software can help us organize our measurements as we get closer to the end of our design cycle. Here is our S1210 software. Today we're going to talk about how you can use it with your far-field measurements to improve pre-compliance testing. As we see, S1210 software holds lots of tests in a single test plan, so you can organize and automate your testing. Furthermore, you have a configuration summary for each test. An important first step is a correction configuration. Here we have a small correction being made for our far-field antenna on our test. We can also create separate correction files for preamps, listens, attenuators, cables, and other corrections. The scan configuration is where we both turn on limit lines and set our pre-scan and final scan measurement techniques, things like RBW and clear write versus repeat modes. In the segment configuration, we look at each frequency segment and determine the individual settings for that frequency span. We can alter the RBW, the sweep time, the attenuation settings, and the preamplifier settings for each sweep category. Now let's go to the measurement. We have that all set up. We can go ahead and run our test. Here we see several peaks that are becoming close to the limit lines and some that are over the limit lines. Each of these can then individually be tested around that peak in a final scan mode that might give you more quasi-peak data or a closer look at the problem. Once your data is complete, you can add all the report data you need, giving yourself a complete record of how and when your device was tested. You can use S1210 software to build confidence in far-field measurements before sending new products to a compliance lab. There we saw how the S1210 software can help us organize test plans, make measurements, and report data. Both near-field and far-field measurements are critical to radiated emissions testing in a pre-compliant state. Use these techniques to speed time to market and avoid costly changes late in the design cycle.